Yesterday, we defined momentum as the product of an object's mass and velocity. What was the other way we defined it? The kind of everyday understanding, the working definition of momentum, not the real definition, because the real definition is essentially the equation that I just circled on the board. What was the working definition? Yeah, it's how hard it is to stop something. And the reason that we defined it that way is because I think that that helps us to understand what it really means a little bit better than the real definition. But in the end, the real definition seems to come from that. Why is it the product of an object's mass and velocity? Well, because the heavier something is, the harder it is to stop. And the more velocity something has, the harder it is to stop. Momentum is how hard it is to stop something, but it's also the product of an object's mass and velocity. Is momentum a vector or a scalar? It's a vector. Okay, so it has a direction associated with it. We saw in some of the questions that we had for homework last night that there was a vector nature that we had to pay attention to. There's a really good example problem that we're going to do later in class today that illustrates really, really well the vector nature of momentum. What about this other one over here, kinetic energy? Besides a couple variables here, P and EK, besides the 1/2, besides the squared, these two equations actually have a lot in common with each other. Okay, kinetic energy and momentum are both dependent upon mass and V. What's the difference there between mass and V in this equation versus this equation, however? What's the big difference there? What differentiates this one from this one besides the P and the EK and the squared and the half? And we talked about this yesterday. Speed doesn't have a direction. Good. Speed does not have a direction because speed is a scalar. And since speed is a scalar, kinetic energy is a scalar as well. So when you're finding the momentum of an object, pay attention to the direction. When you're finding the kinetic energy of the object, don't pay attention to the object. Let's say I've got two objects coming towards each other. They both have the same mass and they both have the same speed, but opposite directions. Object number one is going this way to the left. Object number two is going this way to the right. What's the total momentum of these two objects as they come towards each other? Let's say the momentum of this gun is plus 10. Going this way. The momentum of this one is 10 in the other direction. What's the total momentum there? 0. Because one's plus 10 and one's minus 10, and we had to pay attention to the direction there, right? But what if we're talking about kinetic energy? This one going to the left has a kinetic energy of 10. This one going to the right has a kinetic energy of 10. What's the total kinetic energy? 20. So the total momentum was 0, kinetic energy was 20. Why did we not add a negative value in there for the kinetic energy? Well, because kinetic energy is a scalar and the direction doesn't matter. We had to pay attention to direction for momentum, and we didn't have to pay attention to direction. Not only did we not have to pay attention to direction, we shouldn't pay attention to direction for kinetic energy. What was that other term that we learned yesterday? It was like momentum, kinda, but yet a little bit different than momentum. Okay? It's inertia. Good. Inertia, first place everybody learned that word was Bill Nye the Science Guy, right? Inertia is a property of matter. Inertia is the tendency of an object to maintain its current state of motion or to resist a change in motion. And inertia is dependent upon what? If momentum and kinetic energy are both dependent upon mass and velocity or speed, then inertia is dependent upon just mass. So in other words, an object that's really, really heavy is going to have momentum only if it's moving. An object that's really, really heavy will have inertia whether it's moving or not, because it doesn't depend upon the velocity of the object. We good there? A couple final questions, and then we'll check over the homework that we had yesterday here. What units would we have M in? Almost always. In fact, there are situations where it doesn't have to be this, but if in doubt, you always want to use this because this always works. Occasionally, you can use another set of units, but the units that we're talking about can always be used. So if in doubt, go with these, Katie? Kilograms, good, kilograms. And velocity or speed in this equation would always be measured in meters per second, good. And momentum would be measured in, what are the units for momentum? Mass times velocity, kilograms times meters per second. All right, what about the units for kinetic energy? Well, we could take a look at the variables there. M is kilograms times V squared is meters squared per second squared, right? But what's another kind of shortcut for a unit for energy? Joules, yeah. 1 kilogram meter squared per second squared is exactly the same thing as a joule. We don't have a shortcut really for this one, okay? That's what it is. There is another set of units you're going to learn here in a couple of days, but it's not really much of a shortcut, not like joules is. All right, homework last night, we had questions 5 to 8 on worksheet number 1. We're going to take a look today at questions 5, 7, and 8. Question number 5 on that worksheet says, a 5 kilogram ball accelerates at a rate of 2 meters per second squared from 1.5 seconds. Calculate the ball's momentum after the acceleration. We're going to assume that it accelerates from rest. I should have told you that. You don't need to worry about little things like that on a test. You understand that when I make up 48 pages of worksheets, it's harder to catch little mistakes like that. On a unit test, things like that don't happen. If you're ever wondering about something like that, the quiz or a test, just ask. And I'll tell you, oh, I made a little typo, or no, that's right. It's the way it's supposed to be. This should say from rest, which I'm pretty sure that probably most people assumed anyways, even though I didn't really say that. Okay, we want to find the ball's momentum after the acceleration. Well, momentum is m times v, right? But we don't have v, so how do we find it? Yesterday, we did an example question where we used vf squared is equal to vi squared plus 2ad to find vf, right? Is that a valid equation for this? It actually is a valid equation. When I say a valid equation, I mean something that we're allowed to try. Okay, any equation that involves acceleration is a valid equation here. In my class last year in Physics 20, we would have called them the Group B equations, the acceleration equations. They're all valid. They just don't all fit. They won't all get you the answer because you might be missing some variables. They're all valid. Can you tell me one equation that is not valid here, that you're not allowed to try to find V here, even if the givens seem to fit? Yep. Oh, you're going to get it there. Starting off okay there. If you were in my class last year, we probably would have called it Group A. Equals d over t. Why can we not use v equals d over t to find v here? Even if we had a distance, we couldn't use v equals d over t here. Why not? You know, we got time, 1.5 seconds. So even if we had distance and time, we couldn't use v equals d over t. Because? Yeah? Because what? No. V equals d over t represents constant velocity. And this isn't constant velocity, right? It's accelerating. So that equation is invalid for this situation. Even if it fit the givens, you can't use it. You have to use one of the ones that involve acceleration. I'm going to probably try for this one. A is equal to delta V over delta T. Rearrange that. I get delta V is equal to A times T. And A is 2.00. T is 1.5, giving me a change in velocity of 3.00 meters per second. Now, I'm not actually looking for the change. I'm looking for the final, right? But if the initial is 0 and the change is 3, then what's the final? 3. If I had $0 and my money changed by $10, then how much money do I have? $10. My final money is $10, right? Same as the change in this case. So we're going to say M is 5.00 kilograms times the final velocity of 3.00 meters per second, which gives me 15.0 kilograms meters per second. The positive here does not mean that it's to the right or east. The positive doesn't mean anything here. Okay, we haven't found a direction because we didn't know which direction the velocity was. Good? All right, let's have a look at question number 7 now then. It says a 1 kilogram rock is thrown up into the air from ground level at a speed of 8 meters per second. The ball travels up to a max height, then returns down to the ground. What's the momentum as it strikes the ground? So here's our situation. Here's our rock that's being thrown upwards at 8 meters per second. What happens to that rock as it rises up into the air? What happens to the motion, Caitlin, of that rock? It loses speed, so it decelerates. It slows down. At what rate does it slow down at? Negative 9.81. It's negative because although it's moving upwards in the positive direction, it's slowing down in the positive direction. That's a negative acceleration. Then it's going to reach a peak height before it starts coming back down. What happens to the object when it reaches that peak height? Yeah, it stops. 0 meters per second, it stops, right? And then it comes back down and it strikes the ground. What speed does it strike the ground? Yeah, think about it. If it's moving at 8 and it slows down, let's say it slows down at neg 10 for argument's sake, right? Neg 9.81, close to neg 10. So let's just say it's neg 10. It starts at 8 and it slows down at neg 10 and then it stops. And then it speeds up as it comes back down at neg 10. Then it's got to be moving at the same speed at the bottom as it was when it started, right? The final velocity is not 8. The final velocity is negative 8. The final speed is 8, right? The final velocity is negative 8. So we want to find that final momentum. We're going to say it's m times the final velocity, 1.00 kilograms times negative 8 meters per second, which gives me negative 8.00 kilograms meters per second. Or you could have said 8.00 downwards. How many people did it this way? You used kind of logic to determine what VF was. All right, how many people actually calculated the value of VF? Okay, how'd you do that? There's a couple ways. What was your way? Okay. Somebody that got the right answer. Do you want to? There's a couple ways. One of the ways is to say VF squared is equal to VI squared plus 2AD for the whole trip, from start to finish. We know what VI is. It's 8. VF is what we're looking for, right? What would A be? 9.81. Well, wait. It's neg 9.81 as it goes up, but is it neg 9.81 as it goes down? As it goes down? Yeah. It slows down in the positive direction, and then it speeds up in the negative direction. So there's two variables there, right? Direction and speeding up, slowing down. If you're speeding up in the negative direction or slowing down in the positive, either one of those gives you a negative acceleration. So for the entire trip, the acceleration is neg 9.81. What's the displacement over the entire trip? 0, right? Because you end up back where you started. So then 2 times 9.81 times 0 is 0. So VF becomes the square root of 8 squared, which is 8. That's the final speed. Now we just have to recognize that the final velocity would be negative 8. So listen, I don't care. Use the logic that I use to find VF and then multiply it by M, or use some mathematics to find VF. I don't care. Hey, my way that I did first is a little bit quicker. That doesn't mean it's better, just because it's a little bit quicker. They both gave us the right answer, so one's as good as the other. 8 requires us to do a little bit of math to find VF, unlike question 7. Can't just use logic here. The momentum as it strikes the ground is m times VF, but we don't know what V is. Suggestion? Gotta do some math here. The speed, the question was, if you didn't hear that, guys, where did the -8 come from? The last one. The final speed was 8, but the final velocity was moving downwards, so the final velocity would be -8 or 8 down. Right here? No, sorry, that's just an equal sign right there. So equals 8. No, you couldn't get a negative there if you're taking a square root, right? You couldn't get a negative. Right? Is that good now? Okay, guys, we know that there's one equation that I can't use here, v equals d over t. That doesn't mean you can never use it in the context of momentum. It just means that when you're accelerating, you can't use it, okay? We're accelerating here, so we have to use one of those acceleration equations. Probably this one again, I think. But let's just analyze the trip down, the downward trip. If that's the case, if we're analyzing just the trip down, what's VI? How fast is it moving right here when it starts its downward trip? Good. So VF becomes the square root of 2 times negative 9.81 times the displacement of? No. If we're analyzing just the trip down, the displacement isn't 0. It's -7. Good. Now, when we do that math, it works out to be 11.71921. What have we solved for here? Quick. Hannah, what have we solved for there? Close, the final speed. Yeah, the final speed, not velocity. What's the final velocity? Yeah, 11 down or -11, right? So let's say this is 1.50 kilograms times -11.71921, and it gives us -17.6 or 17.6 down. Good.